Let me finish the topic before the midterm. The Roth stability criteria that we started last class. And then I'm going to teach you some tools. Refresh your mind for the midterm. Okay. So you saw that we had two criteria that the old coefficient must exist and positive for the closed transfer function denominator. And then we had to make a table with some exceptional cases that we discussed in the previous class. And now, if this is going to help you to eventually to help you, if I said if you have this or this system for the controller, s cubed plus k1 s squared plus 2k2 plus 5. Now the question is that for which range of k1 and k2 y over x or closed transfer function is stable. I mean the system is stable, that's right. So as I taught you in the previous class, first of all, the old coefficients 1, k1, 2, k2, 5 must be positive. So 1 is positive, 5 is positive. So the first condition, 1, is k1 and k2 must be positive. This is the first condition. So if k1 or k2, either of them is negative, you are done. Your system is unstable. Clear, everybody? Now 2. 2 was the table that we did together. S cubed, s squared, s1, and the s0. So this is how we were doing, see? Sorry guys, this is s here. I don't know why I forgot that. This is s. Let me, s. So you see 1, k1, k2, and 5. So k1, k2. So now s cubed. So this is how we were doing, right? This and this, and this and this. So you're gonna have 1, 2, k2, and the second line until this point, k1, 5, and you know the last line is what? You tell me. Last line is 5. Now you have to make the table from whatever I told you. This multiplied by this minus this multiplied by this divided by this. So you're going to be 2k1 k2 minus 5 over k1. So the condition was saying that the first column must be positive. So 1 is positive, 5 is positive, k1 already is positive. So this must be positive. So 2 k1 k2 minus 5, this must be positive. So we already established k1 is positive. So this must be positive. So being said that k1 k2 must be greater than 2.5, 5 divided by 2. So the condition of this system with these parameters is that k1 is greater than 0, positive, k2 is positive, and k1 and k2 is greater than 2.5. So this is going to help you after adding the PID controller after spring break. You know that for which range of the system, the gain of the PID controller must be in which range. See what I'm saying? Okay, that gives you a stable system. Okay, so suppose that I'm going to select two sets of the numbers. I'm going to say k1 is 1, k2 is 2. So test check. K1, K2 is gonna be 2. 2 is not greater than 2.5, so your system must be unstable here. Means you have a right-hand side pulse. Let me check that by MATLAB. So when you go to MATLAB, so 1, 1, 4, 5 gonna be. 1 is K1 is 1, K2 is 2, 4, 5. So you're gonna see that by selecting that, you're gonna right hand side pulse of the system. Let me pause this. So, you know that in the previous class we were doing this. You know that the MATLAB workspace typically can remember what you have done until you clear it. Okay, so sims X, I don't know because in the last class we were doing that. Okay, and it was okay. So solver here was 1. What was that? 1, 1, 4, 5. 1, 1, 4, and 5. See? So it has a pair of complex conjugate poles in the right hand side plus 0.0925. See that I selected the K1 and K2, which is not satisfying this stability condition, and you're gonna have this. You have this pulse, a pair of this. What was another one? Called real number or complex? Real number. And here we go. See? Imaginary and the real. So obviously this is unstable system because of this right hand side. Even you now you know it in MATLAB. I'm gonna have some num third order system 0, 0, 0, 1, and then is 1, 1, 4, 5, and then I say step num and then step response. No doubt you're gonna see unstable behavior. Right? Here we go. See? We want to go to the 1. This is 1.5 to 10 to the power 27. You want to go to step function, unit step function, but your system is completely unstable. Now, if you select, let me go back to this page. Now, if you select, next page, the other set, K1 is 1, K2 is 3, so K1, K2 is 3, and 3 is greater than 2.5. See, is greater than 2.5. Bingo. So we're gonna have this time all poles must be in the left hand side. So 1, 1, 6, 5. This gonna K2 is 3. So I'm gonna go back here. This is gonna be 1, oh, not this. 1, 1, and here is 6, 5. The only difference is this adjacent. So you see all the poles are in the left hand side. Negative, real, and a pair of complex conjugate in the left hand side. And if you go Only denominator is changing. Here I'm going to put 6. Now if I say step none and then, you see all goes to here. And following the step function. There we go.
Professor?
Yes. Yeah, okay. Let me show you exactly as it is, huh? Here we go. I'm just putting solve. Okay. See what we get. Can you read it? Double changing to the to numerical to numerical numbers. See what I'm saying? So if you say a 1 and 1 shows this again. So but by putting double, change it to even eval means evaluations. Does the same. Okay. Say if I say eval means evaluations. There we go. Oh, this is 3. I'm sorry, this is 3 solutions. Not just make double. Okay. Double makes the to numeric numbers. Okay. Here we go. So you saw that, right? Selecting the parameter range based on this Roth stability criteria, your system is stable and is underdamped, right? I thought this is because you have overshoot, and it's very underdamped because your damping ratio is very low, so you have lots of oscillation before settling down. And I'm going to teach you later after the break how to design the controller, PID controller, so that we have this profile. Say, here we go. Okay, understand everybody? So let me go to the last problem, and then I'm going to teach you a thing about the emitter. We're done with this. So you say if y over x is 1 over s4 plus k1 s cubed plus k2 plus 3 s square plus 10 plus k3. Suppose you have such a system that after linearization and coming to linear control domain, you're not sure about K1, K2, and K3, or you are adding controller. First, you have to know the range of the stability for this system. Obviously, based on the first condition, K1 must be greater than 0. K2 plus 3 must be greater than 0. Means that K2 must be greater than minus 3. This is second condition. First condition. 10 is greater than 0 and K3 must be greater than 0. So these are conditions. But not enough. What? You have to make the table. Gonna be S4. Gonna be S4, S cubed, S square, S1, and S9. You know how we select them. This and this. And then this and this. Writing here gonna be 1 K2 plus 3 K3, and the second line gonna be from here again, K1 and 10. Obviously here is 0. You know the last line coming from here, K3 always. There we go. Now you have to make this. Let's make that together. So K1 in K2 plus 3 minus 10 divided by K1. And now here, K1, K3 minus 2 divided by K1. So here's going to be K3. first this by this minus this by this divided by k1, then this by this minus this by this divided by k1. Now this line S1, we go for this. So this by this gonna be 10 k1 k2 plus 3 minus 10 divided by k1 this by this minus this by this minus k1 k3, all of these divided by what? I'm saying is a by a. There we go, we got that. So the first column must be positive. This is first column. Here we go. First column must be positive. K1 is greater than 0, we already got that. K3 must be greater than 0, we already got that. Now this. So K1 in K2 plus 3 minus 10 divided by K1 must be greater than 0. We already said K1 is greater than 0, but this is greater than 0. So the fourth condition is K1 in K2 plus 3 must be greater than 10. This is fourth condition of stability. We got it? So this is first condition, second condition, third condition. This is fourth condition of that. Now this. When this is greater than 0, so your a in the denominator here must be, so this must be not greater than 0. What? 10 k1 k2 plus 3 divided by k1 minus 10 must be greater than k1 k3. I'm moving here to the other side. So this is stability number 5 relation. There we go. 5. So now any numbers that you are giving to the gain of the controller, say, or your system is that you don't know about the range of the parameters. So you have to select that these conditions 1 to 5 is being satisfied. For example, I say, okay, I'm selecting K1 as 1. And now going there, first K2 must be greater than minus 3. Okay, so K2 cannot be minus 4, can be minus 2. If I select K2 minus 2, gonna be 1. 1 by 1 is not greater than 10. So you see, I have to select the number. So say K2, I'm saying is again 1. Let me select that. 1 in 4 is 4. Is not good number. So I have to select what? Even select 6, it doesn't work based on K1. So you have to say 7, it doesn't work. So K2 must be 8. 8 plus 3 gonna be 11. 11 by 1, 11 greater than 1. So these two bingo until this point. So K1 is 1, K2 is 8. Got it? What about K3? So let me implement numbers here. 10, K1 is 1. So this is gonna be 1. 1 greater than K1, K3. Okay. See, this is K2 is 8, 11 minus 10 is 1 divided by 1. 10 by 1, 10. So we know that K1 is 1, we selected. So we say 10 must be greater than K3. So K3 can be any number. I say K3 is, I don't know what you say, 5. By selecting these numbers, your system is stable. I'm just giving some examples. Okay. Yeah. So let me try this to see the rough stability. What gives us? So it's gonna be 1, 1, 11, 10, 5. 1, 1, 11, 10, 5. So it's gonna be x4 plus 1 plus 11 plus 10 and 5, right, everybody? 1, 1, 11, 10 and 5. And obviously double. You see, had fourth order system, all of them in the left hand side, minus 0.4, minus this. So you see 2 pair of complex conjugate poles. Bingo. So that works. Even that I want to plot its num, I have to add, this is fourth order system, and then 1, 1, 11, 10, 5. I'm pretty sure that it's gonna give us a stable system. Obviously gives us, see? Underdamped kind of, and finally this. You got it? Step response. Amplitude time. Even that you want to say go for body of this kind of system, I mean the frequency response. I mean input to the system is not the step function, it's the sine omega t. As long as your system is stable, here we go. See, maximum overshoot, and then this is the phase. Okay, now you know everything. So, okay, I'm done officially with the growth stability criteria. Only for midterm, guys. Remember, for the example, in the beginning of this class, at the class 1, I was talking about the equilibrium point. And I told you, you have in your notes, if you have a given, remember the pendulum problem? Remember that? This was the pendulum problem, right? And I said, for find the equilibrium point, what you're going to do? You're going to say bye-bye to transient term. Transient term has time derivative, theta dot, theta double dot. If your system is x dot, x double dot. If your system has y, y dot. If you eliminate those and then solve for the state solution, you're going to find the equilibrium point. Remember that you have your notes. I don't want to repeat myself. That theta was 0 equilibrium point of the system. Plus minus pi, plus minus 2 pi. Remember? And whatever. Right? Yes, everybody? So when you see in the midterm, I'm giving you a complex system and asking you that linearize it, you have to linearize around the equilibrium point. First, you have to find the equilibrium point of the system. So you have to make all of these to 0 to find the equilibrium point of the system. For example, if your system is x double dot plus 4x dot plus sine of x equal to, I don't know, k1 divided by 2 minus x, huh? X, huh? Or x squared, say. I'm going to make it complex because I want to expose you to such a problem. And your midterm is a part of real US Navy problem. Okay? So first, this is completely nonlinear system, sine of x. Yes. Okay? But this differential equation is completely nonlinear because sine of x. So finding the equilibrium points to linearize it, you have to say bye-bye to this and bye-bye to this. Okay? Now you have to solve sine of x is equal to, suppose k1 is 1. Huh? 1, 2 minus x2. You have to solve this equation for the equilibrium points for x star. I'm giving you hints because I want to make you expert of MATLAB. How to solve in MATLAB for x here, this equation, I'm giving you the hint, is fsolve command. Go to the MATLAB help and find it. Maybe this has two sets of solutions, x1 and x2. You have to judge which of them, like the pendulum, which of them is acceptable equilibrium points, which of them is not, based on the physics, reality of the problem. But in MATLAB, you have to use this command, MATLAB, okay? This is one hint I want to give you. The second hint is, remember the Taylor series expansion? If you have y is equal to f of x, we were linearizing, linear was like this, f at equilibrium point that you found from here, f solve, plus round f, remember, for pendulum, round x at x is equal to x star, and x minus x star. We are not going beyond this because it's going to be nonlinear. And here's 1 factorial, which is 1. Now, what if your function has two parameters, x and z? X and z. I'm going to give you a hint. So here, Taylor series can be written as this. You have to find two equilibrium points of the system. So going to be f at equilibrium point of x, equilibrium point of z, plus round f. I'm going to give you an example right now. Over round x at where? At x is equal to x star and z is equal to z star. X minus x star plus round f over round z, again at where? At two equilibrium points. X is x star, z at z star, z minus z naught. So your Taylor series, if you have 3 parameters, you have to add third here. If you have 4 parameters, add fourth here. Expanded version of this, when you go to grad school, is Jacobian matrix, but not now in this level. Okay. So example of this, because you're going to use this in midterm. This is, I have to. Okay, suppose your y is this 2i squared divided by k1 plus k2 x. You have an electromechanical system. I is the current, and the x is displacement. And you already found equilibrium point of current and X from differential equations, as I told you. You already found it. So how to linearize this? This is completely nonlinear. I squared divided by X. So linearized gonna be 2I star square. You are replacing from here. Remember? K1 plus K2 X star. These are numbers. You already found it. Remember, based on the formula I taught you. Plus round Y over round I at I star at X star. Now you're gonna have I minus I star. Guys, did I? Yeah, this way. Okay. Oh my God. Okay. Plus round Y over round X at X star numbers. I star numbers. X minus X star. Okay. So we have to calculate these first. Okay. So round Y over round I gonna be from here 4I divided by K1 plus K2X. At where? At this. So you're gonna have 4I star K1 plus K2X star. Let me give you some examples. Say I star you found is 4 amp and X is, I don't know, 10 centimeter or 0.1 meter. So it's gonna be 16 divided by, and say another example is K1 is 1 and K2 is 10. Just numbers, huh? 1 plus K2 is 10 in 10 centimeter, 0.1. So you're going to 16 divided by, it's going to be 1, 2. It's going to be 8. So these coefficients are going to be 8. 8. Now let's go for this. If you sound emitter and if after graduation you're working as a control engineer, round Y over round X from here gonna be derivative of this. So when we say round X means this is constant, only variable is this. So gonna be 0 in this and minus K2 multiplied by 2I2 from high school in K1 plus K2X squared. When you say X, when you say I means only your variable is I. This is constant. That's why I did like this, simple like that. From high school. So if I put the number, it's gonna be minus 10 multiplied by 2 multiplied by 16 divided by 2 to the power of 2 is 4. So this is gonna be 20 divided by 4 is 5. 5 by this is minus 8. 80. If I'm not wrong, right? Minus 80. Or 90. So yes, 90. 20 by 6. 5. Oh, sorry guys, 80, but was 80. So this is minus 80. See, this is powerless of mathematics. And what is this? We're just going to calculate. This is, let me give you as B. B equals 2 multiplied by 16 divided by 2. It's going to be 16. So interesting to know that. Can I go to next page, everybody? Yes. Interesting to note that nonlinear function of 2i squared divided by k1 plus k2x, which we gave a number of 2i squared divided by 1 plus 10x. By using the Taylor-Series expansion by two parameters, we transfer to y of linear of almost 16, if I'm not wrong with the numbers, plus 8, see here, 8, I minus equilibrium point that we found from differential equation, 4, and minus 8d in I minus x displacement. One is equilibrium point that we found it, 0.1. And very interesting, guys. Linear function I, linear function x. So you change this to this. While you have it, then you can go and find the transfer function and this kind of things. And find the poles and this kind of things. We got it, everyone? Yes? Good, so we are done. I'm gonna cut it here. Hopefully I'm gonna send tonight or tomorrow midterm. Let me first can I give you one problem, very challenging. It includes whatever I